Okay, so we've seen what algebraic numbers are and what algebraic number fields are in the past lecture. So now let's try and start talking about these number fields and doing things with them. So we have a new section. This is section 1.5, and it's called Embeddings. So what we're going to talk about here is basically maps between number fields into the complex numbers and how these different maps can tell us something about the number field that we have. So start with definition 1.5.1, which is the following. Let K be a number field. Then an embedding of K is a non-zero, say field homomorphism. I'll denote it sigma, say, from K into the complex numbers. The reason I've used this arrow with a little curly arrow with this thing on the back is to denote that this is an injection. Any non-zero map between fields has to be injective, because if you think of what the kernel would be, the kernel would have to be an ideal, prime ideal, and therefore the only prime ideals in a field is zero. So if you this is true in general. If you have a map from any ring, say, into an integral domain, then the kernel is always a prime ideal. If you're not mapping into an integral domain, then things might not work. But yeah, in any case, you have some map K into C, and this is just to note that I have to note explicitly that it's an injection. This is why I use this curl on the arrow. One thing to note, so here's a remark. The following. Note that since sigma is a field homomorphism, in particular it's a ring homomorphism, we must have, I'll just say it's a field homomorphism. We must have sigma of x equals x for all x in the rational numbers, which is contained in my number field K. So these field homomorphisms have to preserve. They can't do anything to the rational numbers. They have to send them. It has to act like the identity on the rational numbers. And this is just given to you by the fact that, for example, phi of 1 is predetermined to be 1, and then phi of n times 1 has to be n times phi of 1, which has to be n. And then you have phi of x times y is phi of x, phi of y. So if you think of what happens to two rational numbers, this will mean that rational numbers have to just be fixed. In any case, this is just something to note, that under these embeddings, the rational numbers will always be fixed. And okay, as an exercise, you can check if you want that that field embeddings are always injective. Now, if you recall, I made when I defined my number fields, I said they were subfields of the complex numbers, which were a finite degree over Q. What this means is that we always have at least one embedding, which is just the identity embedding. So note, since our number fields are always assumed to be contained in C, we always have at least one embedding called the standard embedding, or standard or identity. So we're i.e. we're always assuming that K lives is some subfield of the complex numbers. So we have this map from k into the complex numbers, which say for sigma of alpha is just alpha for all alpha in k. This is the identity or the standard embedding. Okay, so let's look at some examples of embeddings, of other more interesting embeddings. So example, is our favorite field at k equals q kb q root 2. Then in this case we have two embeddings. What are they? Well, let's go sigma 1 and sigma 2. This goes from q root 2 into the complex numbers. This one is going to go from q root 2 into the complex numbers as well. And how are they going to be defined? Well, here I'm going to send all my elements in q root 2 look like a plus b root 2. I'm going to send this to just a plus b root 2. So this is just the identity embedding. Nothing happens. And in the other one, I'm going to do something interesting, which is I'm going to send this to a plus b, well, a minus b root 2. So I'm sending root 2 has been mapped to minus root 2 in this case. So note that since embeddings always have to keep the rational numbers fixed, they can only do something interesting is on like the algebraic numbers. On these algebraic numbers, not in Q. So the a plus b always have to map to a plus b, but the only choices that I could think of is going to be from root 2 is going to either keep root 2 fixed and it stays the same, or I change root 2 for minus root 2. And I haven't proved this yet, but we'll see in a bit that when you have an embedding, it's always going to have to send an algebraic number to one of its conjugates. So here it's the first one just sends root 2 to root 2, and the other one says root 2 to minus root 2, and root 2 and minus root 2 are conjugates. But let's continue with this example and somehow extend this. So now let L be this field Q root 2 root 3. So if I join these two elements, this is a degree 4 extension of Q, and it has a basis. Here's one possible basis. Given by 1, root 2, root 3, and root 6, i.e. every element of L can be written as a plus b root 2 plus c root 3 plus d root 6 for a, b, c, d in the rational numbers. Okay, so let's consider what the embeddings of this field are, and then we're going to compare them back to the q root 2. So notice that q root 2, my field k lives inside of L. This is a subfield. So I'm going to describe the embeddings of L now into into complex numbers and see how they compare to the ones that I've defined already. So the embeddings of L are leave a bit more room so you can keep seeing the questions. So I'm going to write this as new 1, new 2, new 3, 4. This is new or eta, I can't remember. Maybe it's V1. Anyway, like this. So this is going to be. I'm just going to tell you what it does. A plus b root 2 plus c root 3 plus d root 6. It's just going to map to the same thing. So this is going to be the identity one. This is where I can use. So it's the advantage of using an iPad, I guess. Let's do the other ones. So what am I going to do? So as I said, the rational numbers have to stay fixed. So my A, B, C, D's can't change, but what can change is these roots. And although I've not proven this yet, I said you can only send a root to one of its conjugates. So the conjugates of root 2 are plus or minus root 2, root 3 are plus or minus root 3, and well, root 6 is going to be determined by what I do from root 2 and root 3. But again, the conjugates would be plus or minus root 6. So like in the first one, we can just send a root 2 to its conjugate. So I can send this to a minus b root 2 plus c root 3 minus d root 6. Notice that because root 6 is root 2 times root 3. When I've changed root 2 to minus root 2, then root 6 has to change to minus root 6. I can do the same thing, but now with root 3. Minus c root 3 minus d root 6. And then lastly, I can do both of them. I can send root 2 to minus root 2 and root 3 to minus root 3. And I get the following one. A plus b root 2 minus c root 3 plus d root 6. So we have these 4 embeddings, and turns out that, we'll prove this in a minute, that the number of embeddings that you can have is exactly the degree of your field. So this is the degree 4 field, we're going to have 4 embeddings. But then let me do what I was going to say. So note that K is contained in L, so my field, i.e., this is inverse, Q root 2 is contained in Q root 3 root 2, which is a field. Obviously just take C and D to be 0, right? Then all of the elements, if I always take C and D to be 0, then the elements just look like A plus B root 2, which is exactly Q root 2. We have this. So it makes sense what we can do is we can restrict those embeddings to K. So I can just say, well, what does this embedding say when I restrict it to just this bit of my map? I.e., I imagine that I'm putting C and D equal to 0, and I'm just restricting to this. So I just look at what this column maps to in this column. So we can restrict these i's to K, and we see that so you want to use the first this is 1 and 3 both restrict to the identity or the standard embedding embedding of K. Notice this, so A plus B root 2 here looks like A plus B root 2, and A plus B root 2 here again stays like A plus B root 2. So when I restrict it, they stays the same. And then 2 and 4, so it's the identity embedding of K, which we denoted above as sigma 1, both restrict to sigma 2. So there is a general result which says if you have a field extension, say Q to K to L, like we have here, then the number of field embeddings of L is going to be its degree over Q, which is 4. The number of embeddings of K is going to be 2, and the number of extensions of embeddings, so how many ways you can extend an embedding from K into L, is going to be the degree of L to Q divided by K to Q. So in this case, it's 2. So each of the talking about restriction. These two restrict to the same embedding. The same thing as saying, well, sigma 1 extends to these 2 embeddings, and sigma 2 extends to these 2 embeddings. So this leads me on to the following definition. Definition 1.5.5. So let K over F be a finite extension of number fields. number fields and let sigma from F into the complex numbers and U from K into C be embeddings. Then we say eta extends sigma if eta restricted to F is the same as sigma. Symbolically, in symbols, we say eta eta restricted to F equals sigma. So this line F just means restricted to F. It's like a vertical line. So this is what I want to mean when I say I've extended my embedding from one to the other. So in this case, as I say, sigma 1 extends to eta 1 and 3, and sigma 2 extends to eta 2 and 4. Okay, so now let's start talking about what these embeddings do. So how do you construct them? I've told you that they exist, and we've looked at some examples, and I've been constructing them by changing the roots of polynomials. So start making more precise the stuff that we've seen in this example. So proposition 1.5.6. So let K over F again be a finite extension of number fields. Oh, I guess I don't need to be finite. Be an extension. And sigma from K into C. No, I think I do want let's do finite. Extension number fields. Sigma from K into C be an embedding such that sigma restricted to F is just the identity. So it's an embedding which just keeps whatever is in F fixed. So id represents identity embedding. Then if f of x is in fx is an irreducible polynomial, and alpha is one of its roots, then sigma sends alpha to a conjugate of alpha. So I guess, yeah, I go back and say I actually don't need this to be a finite extension. Any extension, I'm just assuming that there exists some field where the roots are. So, let's prove this. Proof. So let's just look at what the polynomial is. Let f of x, let's assume f of x looks like a0 plus a1x plus dot anx to the n. Then since sigma fixes f, so if I fixes f means it doesn't move f around, it's the identity on f. And since alpha is a root, so we have a0 plus a1 alpha plus an alpha to the n equals 0. It follows that if I just apply sigma to this equality, sigma of a0 plus an alpha to the n, this is sigma of a0 plus sigma a1 sigma of alpha plus sigma an sigma of alpha to the n, which because it fixes the elements in A0, here the elements right as AI then in F. So this is A0 plus sigma plus A1 sigma of alpha plus an sigma of alpha to the n. But this is equal to 0, so this equals to 0. Therefore, sigma of alpha and alpha have the same, well, satisfy the same polynomial. So the conjugate. I've not taken f to be the minimal polynomial, but you can take it to be. It's not going to matter. If I take f to be the minimal polynomial, then sigma alpha is going to be another root in its minimal polynomial, and by definition, these were conjugates. So I'm just maybe I'm lying a bit and extending this from minimal polynomials to all polynomials for by definition of conjugate, but this isn't the big thing. But anyway, yeah, the key is that because this is a ring homomorphism and it fixes f, then if I have my my integral dependence relation for alpha, then if I apply sigma to it, I just get the same integral dependence, but now for sigma of alpha. Remember that sigma of alpha is now some other complex number. So I have this other complex number satisfies the same polynomial. So they have to be the be conjugate roots. So yeah, if you're going to write down an embedding, then you need to somehow think of find all the conjugate roots of your polynomial and move them around. So here's a important lemma to do with these embeddings and how many. Well, this is going to help us to decide how many embeddings we are, but this is called the separability lemma. You may have seen this in Galois theory. So this is lemma 1.5.7. It's called separability lemma. What does it say? Well, it tells us something that doesn't work for like finite fields, but it works for these number fields, which is that if you have an irreducible polynomial of degree n, then it has at least it must have n distinct roots. This is actually quite important, and this isn't true if you have like irreducible polynomials over finite fields. But for number fields, it's true. So let K be a number field. And f of x and kx, an irreducible polynomial, an irred poly of degree n greater than or equal to 1, then f of x has n distinct roots. Moreover, if sigma from k into the complex numbers is an embedding, and I'm going to denote f sigma of x, the polynomial that you get by just applying sigma to the coefficients of your polynomial. So this is now a polynomial in k of x, and this is an embedding of sigma from k into c. So sigma does act on k; it does move k around. So this actually is not just identity. In the previous example, we were assuming that sigma restricted to f was the identity. So this is why these AIs stayed the same. But in our new one, we have a polynomial over k of x, and this is an embedding from k into c. And if it's not the identity embedding, which it could be, then this polynomial is actually going to be something different. So I'm going to let f sigma of x be the polynomial we get by applying sigma to the coefficients of f. Then f sigma also has n distinct roots. Great, so let's do this proof. So we start with the fundamental theorem of algebra. So by the fundamental theorem of algebra, FTA, I guess. Maybe that's a bad one because it's fundamental theorem of arithmetic. Maybe. Fundamental theorem of algebra. F of x in this is a polynomial of degree n. This has n roots in the complex numbers. So we only need to show we have no repeated roots. And this is where the irreducibility is going to be playing a key part. The fact that it's irreducible means that we know that it's going to have at least n roots, but all of them have to be distinct because otherwise the polynomial wouldn't be irreducible. So here's the trick for this. We consider the derivative f dashed of f, which is also in k of x, and it's also non-zero. It's non-zero because I assume that the degree of my polynomial was at least 1. So this polynomial, but the derivative has degree, has degree 0, but it's not the number 0, because if my polynomial was constant, then when I differentiate it, I get 0. So it's something of degree 1. So when I differentiate it, I get something at least, could be a constant, but it's non-zero. So now note that if f had a repeated root, then f and f primed would share a common factor. Notice, think of this as, well, if f of x has a root, say alpha, so I write this as x minus alpha to some, and I'm assuming it's repeated, so I have something like some power a, and then I have some other polynomial, g of x. If you consider what the derivative now looks like, so f dash of x, I have a, x minus a minus 1, g of x plus x minus a to the a, g dash of x. And now if you think of what, so, I put a's when I should put alphas. Minus alpha. If you look at them, then f of x has alpha as a root, and clearly f prime of x also has alpha root, because I'm assuming it's a repeated root. So repeated root means a is greater than 1. So this term a minus 1 is at least greater than 1. And a is like 2 or above. So this term is always there. So both of these things have a root. So they share a common factor, these two polynomials. So they have a common factor, which will denote by h, say. So now let g be the greatest common factor of f and f primed. So these are two polynomials in f of x and k of x. It does make sense to talk about the greatest common factor. We have this division algorithm, right? So we can do this division algorithm, and we can make sense of what it means for greatest common factor of two polynomials. So let g be the greatest common factor. Then the degree of g has to be less than or equal to n minus 1, because this polynomial f primed has degree n minus 1, and it has to divide f prime. So it's whatever degree it has to be at least n minus 1, and it divides f. But f is irreducible. So g must be constant. can't be the whole thing because the degree of f is strictly smaller than n. So it's n minus 1, at least n minus 1. So g must be constant. So the greatest common divisor must be constant. But then h has to divide g as well. This means h is also a constant. Therefore, f and f prime don't have a common factor, or don't share a common factor, which is what h was. This means they don't share a common factor. So if they don't share a common factor, they couldn't have been a repeated root. And this finishes the proof for f, and the same proof works. So the same proof works for f sigma. You do the same thing. So you get the result. I checked that I have at least n roots, and I checked that if I were to have a repeated root, then f and f prime would have to have some factor in between them. So some like x minus a to something would be a common factor. But I've just checked that f and f prime have to be coprime. So this can't happen. Great. So how is this lemma useful to us? Well, it tells us immediately how many embeddings we can possibly have. So here's the proposition. 1.5.8. For every embedding, say sigma from f into the complex numbers, there are degree k over f embeddings of k that extend f. So if you come back to this example that we had up way up here, I had my field L, which is degree 4, and inside it I had my k, which is q root 2, and this is telling me that the number of ways extending from embeddings from k into L is the same as the index of k and L, so k to L, L to k, which is, in this case, this is degree 4, this is degree 2, so it's just 4 divided by 2, which is 2. So this is how many ways you can extend an embedding. Once you have an embedding of your smaller field, how many ways can you turn it into an embedding of the bigger field? So this is a proof. We're going to do this by induction on the degree of the field. So on this degree, if k equals f, there's nothing to prove. So assume that k is different than f, and sigma is an embedding of f. Now let's take some alpha, which is in k, but not in f, right? I can do this because I'm assuming that k and f aren't the same, and I'm guessing I should say k is an extension of f, so k is bigger than f. So I take some element alpha, which is in k but not in f, and now let's consider its minimal polynomial over f. Min pol over f, which we denoted by m alpha f. Now let beta be a root of the polynomial you get. Oh, we've already introduced the notation. The polynomial, a root of m alpha beta, but now I've applied sigma to it. So remember, this is what this notation meant. I take m alpha, which is my minimal polynomial, and to every coefficient I apply my my embedding sigma to it. I get a new polynomial, sigma. And thing to note that this is the same thing as m alpha f sigma, where f sigma is the image of f under sigma. So sigma is a field homomorphism. The image is going to be a field. F sigma is just my notation for the image, the field that you get after you apply sigma to it. So remember, sigma goes from f into complex numbers. So this statement, this line here is telling you that if I take the minimal polynomial and apply sigma to all the coefficients, I get the minimal polynomial of alpha, but now over the field whose entries are, are in f sigma. We have this. Since m alpha of f is irreducible, and so is m alpha f sigma. So these are two different irreducible polynomials, and remember that beta is a root of this polynomial. So now, by theorem, so we have this theorem 1.3.4. We have the following. So we have f of alpha. This is isomorphic to fx modulo m alpha of f of x. This is what this theorem was telling us. Now, by using my embedding, this is the same thing as f sigma of x. The polynomial is now in f sigma divided by m alpha sigma of f, which is isomorphic by this equality here, and the fact that beta is a root of this polynomial. This is the same thing as f sigma x modulo m beta f sigma. Isomorphic to this field. Notice that alpha and beta are both roots of this same polynomial in this field. So they're conjugates, so that they have the same minimal polynomial. So I can change my alpha to my beta. This doesn't change anything. But now this is isomorphic to f sigma of beta. So therefore, we have an isomorphism. This is isomorphic to f sigma of beta, which sends this isomorphism is given by sending alpha. Sends alpha to beta, so it sends one root to the other, and restricts to sigma on f. So this isomorphism that I've written down sends alpha to beta, and then when I look at what it does to the elements at f, it just sends f to f sigma, so it acts as if it was sigma. So if we now do this for each root of this polynomial, m sigma alpha f, we get the following. So doing this to each root m alpha f sigma, we get a bunch of different isomorphisms like this, which gives us a bunch of different embeddings. So doing this for each root of this, we see that there are the degree of m alpha of f, which equals this degree. We have this many extensions of sigma to f alpha. This is how many extensions we have, because think what this isomorphism is doing. It's keeping, it's acting on f as if it was sigma, and it's just changing alpha and beta as around. So now we have this many extensions from here to here, but now we just use the inductive hypothesis. I'm guessing when I say by induction, I meant let's do it by induction on this degree. So let's assume that I know it for every field which has degree smaller than this. So this is now some subfield of K, which is something smaller. So I've proven it for this. And you can just work it out. Okay, great. So we now know how many different ways you can extend an embedding from one field to the next. So let's give some names to these different types of embeddings. Oh, this should be enough. So here's a definition. This is 1.5.9. We say an embedding is real if its image is if it lands inside the real numbers inside of the complex number. So the embedding has to go from F into C, but it might not. So embeddings have to go from, like, say, from your field into the complex numbers, but it could be that they don't have to land in the complex numbers. It could be that it lands in something smaller, which is like the real numbers. So in this case, we say that the embedding is real because its image is in fact inside the real numbers, inside of the complex numbers. Otherwise, we say the embedding is complex. And note that if sigma is a complex embedding, then what I'm going to do it by sigma bar, this is the embedding you get by composing sigma and complex conjugation. So then sigma bar, which is, well, let's say the map you get by composing sigma and complex conjugation is again an embedding. So if I have a complex embedding and I do complex conjugation, then I get a different complex embedding. You could try to do this for real embeddings, but nothing's going to happen, right? Because complex conjugation acts trivially in the real numbers. It's nothing. So we call sigma and sigma bar a pair of complex conjugate embeddings. The previous proposition, so here's a remark that follows from this definition, the previous proposition. Note that if we have, say, K over Q, a finite extension, and R1 equals the number of real embeddings. This is going to be standard notation. R1 will always mean, for some field, usually you can do R1 the number of real embeddings. Okay, and R2 the number of complex conjugate embeddings. Oh, complex conjugate. So I take them and I just pair them up, sigma and sigma bar. Then what the above proposition told us was that this equals R1 plus 2 R2. So I said the number of ways extending embeddings was the degree of the field. Now if my base field here was Q, then there are no embeddings, and the number of ways of extending the identity embedding from Q into C is going to be the degree of K into Q. So this tells me that the number of embeddings of K over Q is the number of real embeddings plus twice the number of complex conjugate embeddings, because I've paired twice the number because I've paired them up like this. Okay, and let's finish this off with An important theorem which follows from all of this. So theorem 1.5.11, which is the primitive element theorem. So this is one of our more important results. We'll use this a lot without even thinking. So what does it say? K over F be a finite extension of number fields. Then there exists some alpha in K such that K is isomorphic to F of alpha. Remember, this is what we call the simple embedding, sorry, a simple extension. And alpha was called our primitive element. This is why it's called the primitive element theorem. It says that if I have any finite extension, then I can always find one element such that K just looks like F adjoined that one element. So how are we going to prove this? So proof. Again, we're going to do this proof by induction. So we argue by induction on this degree. So if K equals F equals K, then there's nothing to prove. So just like we did before, so assume that K is different from F, and I'm gonna let alpha be some element of K take away F. So this is the bar is the line is going the other way. This is this F, remove the F from K as sets. Then what does this mean? Then by our inductive hypothesis, we have K has to be F of alpha plus beta for some beta in K. So we have some finite extension. So I know that I got it from adjoining some finite number of elements. And I assume that it's, let me just put this on this side. K looks like something like F alpha 1 alpha n minus 1 adjoin the alpha. This field I can write this as F alpha by this what we saw in the tower law. I can write this as F alpha 1 alpha n minus 1 adjoin alpha. But now this is some field of smaller degree. So because I'm doing an induction on this, I can assume that this field is just generated by, instead of using n minus 1 things, I just have one element, beta. So this is just F of beta, and then this is F of beta join alpha. So this is why my field looks like this. So I know that my field K looks like F of alpha plus beta. We claim that there are infinitely many numbers C such that C such that K is F of alpha plus C beta. So we claim that this is that I can find infinite many C's such that this linear combination is the whole field. So I'm going to prove that there's only finitely many C's for which this couldn't hold. So we will show that there are only finitely many C for which K is not F of alpha plus C beta. So there's only finitely many C's that don't work. So let's assume this is the case, and let's think about how many conjugates this element alpha plus C beta has. So assume this is the case. Then yeah. If we had f equals, if we were in this situation, then by proposition 1.5.8, there would be this many conjugates of this number. But because we're assuming that this isn't the case, we must have less of them. So since we are assuming k is different from f alpha plus cb, there must be fewer. Fewer conjugates. In particular, what does this mean for embeddings? In particular, we must have two distinct embeddings say sigma and eta, say from k into the complex numbers, which extend from f, and send alpha plus c beta to the same element. So I must have, because I have less conjugates than I should have, then I should have two embeddings from k into c, which somehow extend from f, so they keep f fixed, and they have to send this. They both have to do the same thing to this element. So I must have sigma of alpha plus c beta equal to eta of alpha plus c beta. Remember what this is? This is just eta of alpha plus c. Oh, I should have said this. C and f. On this side, this looks like this, and this is sigma of alpha plus c sigma of beta. So we have this equality, and now note that sigma of beta has to be different from eta of beta, since otherwise, if we had these two, if this and this were the same, then this and this would have to be the same. Otherwise, sigma of alpha would equal eta of alpha, and therefore, since we're assuming that k is this field, we'd have we would have sigma equal to eta, right? I'd have two embeddings, two embeddings of this field, which act the same on alpha and act the same on beta. If this wasn't the case, so then the two embeddings would have to be the same, but I'm assuming that there's two distinct embeddings. So these two embeddings have to be different, so they have to send alpha and beta to different things. So sigma and alpha, so we would have this, which would contradict the fact that they are distinct. So if I take this long equation here and rearrange to solve for c, so we have, because they're not the same, so because these two things aren't the same, I can rearrange, and I can write c as eta of alpha minus sigma of alpha over eta of, should be the right, sigma of beta minus eta of beta. I'm allowed to do this because, I'm not dividing by 0 because this has to be the case. But now, I I told you that the embeddings, they can only send a root to another conjugate root. So there's only finitely many choices for C, because C has to satisfy such equality, and there's only sigma and alpha can only the choices for where to send alpha are limited in each of these cases. We have this, but by proposition 1.5.6, there are only finitely many possibilities for what eta of alpha, eta of beta, sigma of alpha, sigma of beta can be. So only finitely possibilities for C such that f of alpha plus C beta would be different from K. So there's only finitely made choices which wouldn't work. So if I pick any C which isn't in there, you can actually do this explicitly and figure out what the C, how to find a C that works. But it doesn't matter. We just wanted to check that one check that one worked, and so I claim that there were infinitely many of C such that this would work, and this is the case. I can always find a C such that K equals f of alpha plus beta, but this is now just one element. So my field again has this form of being f adjoined one single thing. And that's the end of the proof. If you done Galois theory, then there's a very easy, much quicker proof of this. You can have a look in the typed notes. I put it right at the end. This theorem is going to be quite important for us going forward. We're going to always somehow use it to just assume that we know what our fields look like, that they look very nice. This will be quite useful for us. But yeah, this ends our section on embeddings, and I'll leave it here for now.